Okay, so the next topic we're going to talk about is what's called transformer EMF. So recall that Faraday's law says that V EMF is equal to negative derivative with respect to time of B dot ds. Okay, so if you look at this equation, we can induce a voltage basically in one of two ways. All that this is saying is that this integral, right, or this whole integral here, right, is going to give you some function which is time dependent. If this function, which is time dependent, changes with respect to time, we're going to induce a voltage. If this does not change with respect to time, we won't induce a voltage. So think about this. We have two different things there. We have B, which could change with respect to time, right? So the magnetic flux could change either in direction or it can change in magnitude. But we could also change the surface area, right? So if you think, if we have the surface area of a loop and we rotate the loop, we then change the normal direction, right? Or we could have it such that we could shrink the loop, right? If we had the one of the sides of the loop on something that could roll, we could shrink the loop or increase the loop, changing the surface area, right? So there's two different ways we can induce a voltage: changing the flux, the magnetic flux, or changing the surface area it passes through. Okay? In the first case, we're going to say, let's assume that the surface area is constant and that the normal direction is constant and that the magnetic field is changing, right? So this is what we call transformer EMF, right? This is transformer electromotive force or induced voltage. And what we mean by transformer EMF is that the magnetic flux density, B, changes with respect to time, but the surface area and the normal remain constant. Okay, so this is the principal operation for transformers. In transformers, we basically have two solenoids on either side of a core, and those solenoids create a cross-sectional area. Now, if you think about a transformer, we have a solenoid which is constant, right? It has a constant area. That area never changes, but we still induce a voltage. How does that happen? That happens because we constantly change the magnetic field, okay? If the magnetic field wouldn't change, you wouldn't induce a voltage on the second side, right? And if you think about a constantly changing magnetic field, the way that we achieve that is with alternating current, right? So if the current keeps alternating back and forth and it changes its amplitude, that means that the magnetic flux is going to change with respect to time. This is the exact reason why at DC conditions a transformer doesn't work, right? So if you think about this, DC conditions means we have no change with respect to time. VEMF equals 0 because there's no change. So let's take a look at an example. All right. So again, I'm going to use that same loop that we used before. I'm going to say, well, what if I have this loop and it's an open loop like this? Okay. And I have a magnetic field which is equal to 4T, and this is the AZ direction. So the AZ direction is coming out of the board towards us. And you can see that it's changing with respect to time, right? So it's actually increasing. As time goes on, it gets stronger and stronger. After 10 seconds, we would have 40 Tesla. After 100, we'd have 400 Tesla, and so on. So what we want to do now is we want to find what the induced voltage would be. And we should see here that the induced voltage is going to be constant. And the reason we know that is because we're going to take the time derivative here. If we take the time derivative of a linear function, we end up with a constant function. Okay, so first let's look at this and let's say, what is the rate of change of B with respect to time? When you take the derivative of 4t, you simply get 4az. Okay? And then we know that the EMF is going to be equal to negative derivative with respect to time, B dot ds. And like we said, since B is changing and S is not, we can just bring that in as a partial, and we can apply that right there, okay? So we'll say negative 4 ds. Okay. So if you look on the slide where this example is in the PowerPoint presentation, you'll see that it gives the surface area here is simply equal to 400 centimeters squared. Okay. So now if we put this in, we can see that the magnetic flux is always normal to the surface area there. So we don't have to do any kind of integration. We simply multiply 4 times the area. So we're going to get negative 4 times 400 centimeters squared, which is going to be equal to 0.04 meters squared. Okay? And we multiply that out, and we're going to get negative 0.160, or we'll say 160 millivolts. Okay, this is where I want you to be careful. So the negative sign only means that the current that's going to be produced is going to change, is going to oppose the rate of change. So this flux is getting stronger coming out of the board, so we're going to want a flux that goes into the board to change, to oppose that change. All right, so when we do that, let's think, what would the direction be? A clockwise current would produce a flux going into the board and oppose the change. Okay? If we were to have an induced current, which would be clockwise, that would mean that we have to have a higher potential here than we do here, right? So the induced voltage would be 160 millivolts here, okay? Again, I don't want you to get confused with the negative sign here. You just have to say, what would the positive polarity be to produce a current such that it obeys Lenz's law? Okay. Now the second part of this example says, what if where we had this open circuit, we closed that circuit with a 100 ohm resistor? Well, in this case, we basically have this. 100 ohm resistor here. The induced voltage would still be the same, okay? We have 160 millivolts like that, right? And then we can simply use Ohm's law. We can use Ohm's law that says that I is going to be equal to V divided by R, right? Where V is the voltage drop across there. So 0.160 divided by 100, and that gives you 1.6 milliamps. And it would flow like this, and that would be in the clockwise direction, producing flux that opposes the change of flux here.
Good.